And according to my mark in the book, I had that we were going to do the preliminary questions in 12.4 exercises. Is that right? Oh, that's right. Page 660. Your loose leaf book, that's the entire text. It's not just this. Yeah. Let me ask you, is 12.4 exercise a preliminary question on your page 660 also? Okay. Had a question this morning. The guy was helping, a work study student was tutoring somebody, and they said this was not. Let me see if I can find it. Parts, trigonometric intervals. Yeah. Page 382. Now the 382. Do you have a thing in the margin there, integrating 10 to the mth x secant to the nth x? You do. The woman said she didn't have that in her, because the reason I asked, she said she had loose leaf, not a bound text. She said it's not in the loose leaf. I thought, why wouldn't they put it in the loose leaf? But it's in yours. Okay. Yeah. Okay. Case 1, case 2, case 3. Yeah. I think they must have just missed seeing it. Okay. When I saw, since that happened this morning, I thought I'd ask while I was here. All right, let's look at preliminary questions on page 660. What is the 1-3 minor? Boy, you're getting hit with this all day, aren't you? Of this matrix. And they make it, yeah, this is the one that, I can't keep straight. Yeah, if this is saying determinant, it means they put DET. I don't know. I was going to see. I think they mix their notation a little bit here. So what is the 1-3 minor of that? See, has everybody in this class got a book? Let me think. No, I'm not sure that Faith does. So let me write this down. Let me get the current slide set up. Okay. Here's the matrix in some form or another. Usually when I write a matrix, I put it in the bracket, not in bars. So 3, 4, 2, -5, -1, 1, and 4, 0, 3. Okay? And the question is, what is the 1-3 minor of that matrix? How would you do that? Okay. Remember, this morning we called it the A13. Yeah. Yeah. So that element right there. So what's the minor for that element? Say again? No, okay. The minor for it means wipe out that row and that column, and it's the matrix that's left. Okay, but it didn't ask for the determinant of it, I don't think. I don't think that's what it's asked for. The minor would be this determinant here. -5, -1, 4, 0. Now that's what I understand form the mean by the minor. Let me see if they mean that or if they mean the determinant of it. This is 12.4 preliminary question. Yeah, they mean, and I take it that this text is using the straight lines that look like absolute value bars to represent matrix, not determinant. So I think that's the answer that they wanted, except I write it with brackets. Number 2, the angle between two unit vectors E and F is pi 6. I can't read. What is the length of E cross F? Well, what's one of the definitions for E cross F? And especially when we're looking lengths, magnitudes. E cross F, okay? Now, by the way, these are unit vectors, so I should have put carets over the top, not, whoa, wrong. Okay. See if I can get it right this time. Yuck. Okay. It says, what is the angle? No, the angle between two unit vectors E and F is pi 6. What is the length of E cross F? So when they say length, we're looking for magnitude of E cross F. You remember the definition for that? Okay. Magnitude of E times the magnitude of F times the sine of the angle in between. They didn't give it a name, so I'm going to call it theta. Okay? Well, I think I know what the magnitude of E is. Do you? Huh? Okay. The angle between two unit vectors E and F. 1. All right. 1 times pi 6. Exactly. So the angle between them, what is the length of that cross product? It's pi 6, which you usually don't think of as a length, but it is, because it's 12.4. I'm in the wrong thing. 12.4. Wait a minute. Oh, I'm sorry. I misread the problem. The angle between it is pi 6. So it's the sine of pi 6. Okay, what is the sine of pi 6? That's pi 4ths. Okay. Pi 6 is the same as 30 degrees. Okay, let me show you something about 30, 60, 90 triangles. Always. I don't know if I've got it right, but let's assume that. Okay? If this is 30, this is 60, and this is 90. Okay? Okay. If this length is 1, that length is 2. Do you remember that? Okay. How about this? What if we drew exactly the same triangle down here? Then what would this angle be? 60. This would be 60. So that's the equilateral triangle, right? If you bisect this, let's say each length there is 2, bisect there is 1, right? So automatically, the sine of 30 or pi 6 is 1. It's a pretty handy thing to, so this is 1/2. So the magnitude of that would be 1/2. All right, next, I think, well, let's try writing it down. What is U cross W, They didn't say these were unit vectors, so I'll say U cross W. Assuming that W cross U is 221. What would be U cross W then? A scalar? Huh? Not quite. Opposite, you got it. So what would this be? Absolutely. -2, -2, -1. Okay? And let's make sure they got it right in the back. 12, what is this? 4? -2, -2, -1. Bingo. Or, can't say that in Alabama. Okay. Next. Find the cross product without using the formula. Okay? 482 cross with 482. Any ideas? Say again? Without using the formula. Yep. Okay. I'll let you glance at this formula called its home board. Substitute U and no, we don't have names for them either. But those aren't unit vectors. These are, but that one cross itself is going to be the magnitude of that, whatever that is. Times the magnitude of that, whatever that is. What's the angle between those two vectors? What's sine of 0? Here's just a little, this is what I think of, because I've had physics and you haven't yet, but you will. Dot product of vectors in the same line basically is the square of the magnitude. We had that before, right? Dot product of perpendicular vectors, 0. The cross product of parallel vectors or in the same line, 0. Cross product of this, maximum. Okay. Yeah, they just are exactly opposite of each other. One's sine, cross product is sine, dot product is cosine. So, one is 1, the other is 0, one is 0, the other is 1. Okay. All right, that was the A part. The B part. Same vector there, cross 241. And I will have to go back and change something ever so slightly in the A answer. All right. Marcus is here. Same two I had this morning. Okay. Good to see you both. Yeah. So that means they're in the same direction. So guess what? Say again? The angle's 0. Okay? Yeah, the angle between them is 0. Sine of 0 is 0, so the magnitude is 0, but I think that's all we said before. On these, the zero vector. Remember, our cross product is always a vector. We just said is zero, and I didn't specifically say the zero vector. Both of those should be the zero vector. 2.4 preliminary question. Oh, and in the back of the book, oh no, okay. They say vector notation, but they write 0, 0. Okay. Unless I misread the problem. They should say 0 vector. Okay. They don't. They just say 0, 0. Okay. Number 5. Last clean slate here. Okay, to erase it. We're doing the preliminary questions at the end of 12.4 on page 660. Okay? Now, number 5. What are I cross J? I should say, what is I cross J? Say this again. Yeah. Yeah. K. You got it right. Okay. And then the second part of that is I cross K. Say again? Not quite. Negative J. You got it. Because if you go in order, and you can make it alphabetical order, okay, then they're positive. If you go counter to that, it's negative. So I cross J is K, J cross K is I, K cross I is J, if you keep it in that order. But when you reverse them and go in the opposite direction, then they become negative. J cross I is negative, K, and so on. And we got 3/4 of the class here. That's good. My first class this morning had 2 out of 4. Second class had 1 out of 4, and at least this one got 3 out of 4. Good deal. Okay, that we're doing preliminary questions for 12.4. This is where we left off last time. We've just done the first 5, and let's do number 6. When is the cross product V cross W equal to 0? V cross W equal, and they really should say the 0 vector, okay? Because the cross product produces a vector. When is that the case? I'm going to say 4 possibilities. Say this again. And when is that? Okay. Okay. Now, actually, the way you said it is better than what you said. Okay. When the angle between them is 0, that means they're in the same direction. But if you say it the way you said there, it's actually more precise when they're multiples of each other. Multiples of each other will either be in the same direction or exactly opposite direction, because the sign of 0 is 0, but the sign of pi is also 0. So either of those will work. So the way you said it, when they're multiples of each other, that would be when V is equal to C times W, or W is equal to C times V, or however you want to say it. If there are any multiple, positive or negative multiples of each other, then that will be a 0 vector. Okay? 2 other possibilities. Say again? Yes, if V is a 0 vector, or if W is a 0 vector. Okay. So, any one of those 3 then. I was going to say parallel or anti-parallel, but when you said multiples of each other, that covered both of those. Okay? So let's see, make sure the back of the book said the same. They would be 0 if either V or W or both is 0, or if V and W are parallel vectors. Okay? It's okay too. I like to say parallel or anti-parallel, but the way you said it was actually the best way. That one of them's a multiple of the other. Absolutely right. Okay, number 7. Which of the following are meaningful and which are not? And you'll need to explain these as well. Okay, A. And my pen is not writing, and it's not clear why. Ah, there it right. Okay. It's a delayed write. Okay. U dot V cross W. Okay, B. U cross V dot W. C. That means yes in Spanish. Okay. W. Magnitude W. Times U dot V. D. Magnitude W times U cross V. All right. So, meaningful or not meaningful? A. Meaningful or not meaningful? Does it make sense to do that operation? Can you do that operation? Say again? Okay, let's assume that U, V, and W all are same dimension vectors. Meaningful or not meaningful? Say to me. What is U dot V? What kind of a quantity? It's what? It's what? Scalar? Is that what you said? Can you cross a scalar with a vector? No, not meaningful. Okay, can't cross. You got to cross vectors. You can't cross a scalar with a vector, and that's the scalar. How about this? V. Meaningful or not? Yeah, because this will produce a vector, and you can dot a vector with a vector. Very good. Now C. There's a part of me that wants to say, yeah, sure, there's no problem with it. Because this is a scalar, the magnitude of a vector is a scalar, and that's a scalar. You can multiply any two scalars together. Now, whether it makes any sense for any practical purpose, I don't know that it would, but you sure could multiply any two numbers you wanted to. So I guess you call that meaningful. How about this one? Yeah. You can multiply a scalar times a vector. That'll produce a vector. You can multiply it. Now, I don't know if the book means, does it have any, does it make any, yeah, I don't, what did you say? Yeah, does it have any usage? And I don't know the answer to that. A is not meaningful. Yeah, all three of them are meaningful. Of the last three are meaningful. A is the only one not meaningful because you can't multiply. You can't do a cross product of a scalar with a vector. You only dot or cross vectors. Okay. The other two are just, the other three are just multiplying by scalars. The B is dotting a vector with a vector, which you can do. C and D are both multiplying either a scalar or a vector by another scalar. Okay. Number 8. Which of the following vectors are equal to J cross I? J cross I. Okay. Which of these are? Is I cross K equal to that? Is minus k equal to that? Or is I cross j equal to that? Okay? Which of those is the same as j cross I? A, B, C, A and B, B and C, or all three? Make it right every time. Say again? A? Okay. What is j cross I? Okay. I cross j would be k. Negative k. So we see B is an answer. But what would be I cross k? Negative j. Not the same as that. What would be I cross j? Positive k. So these can't be the same because they're opposites of each other. This is the answer. This because they're actually two different vectors. Okay. So only B. Okay. You better have that right in the back. B. Got it. All right. I think I already had assigned the homework exercises there. Either 1 or 3 or both if you choose. Either 5 or 7 or both if you choose. Either 9 or 11 or both if you choose. Either 13 or 15 or both if you choose. Any of the odds 17 through 21. Do 23. Do 25. Then the rest of these, any of the odds 27 through 47. Then do either 49 or 51 or both. And then 53 through 61. Some of those are just thinking through, writing through, so any of those that you choose to do. And then either 63 or 65 or both. And yeah, stop there. You can also look and see if there's anything in there that might lead you to a paper topic. Right off the top, I saw something about Newton's laws, and certainly if you want to write about Newton or his laws or that kind of stuff, you can. And then I don't see anything special in the others either. Except further insights and challenges, I give you the 3x3 diagonal rule that we did in linear algebra this morning for those two people. So, all right, we're ready for 12.5. Any questions? 12.4. All right, 12.5. Planes in 3 space. A linear equation, this is doing a little background stuff here. AX plus BY is equal to C. Okay? Wish they hadn't said that. What kind of equation is that? Linear equation, exactly. They said it and I said it, okay? What makes it a linear equation? Has 2 variables, that's good. That's not enough. What makes it a linear equation? Any equation could have 2 variables. What makes it? Yes, the maximum exponent. The only exponent allowed for the variables is 1. 1 and only 1. If one of those was a squared, you'd have a parabola, not a linear equation. That would be a quadratic equation. If one was a cube, you'd have a cubic equation. So that what makes us a linear equation is the exponents for the variables can only be 1. Okay? Now, that defines 2 variables. That defines a line in R2. 2 space. 2 variables means you're in R2. Okay. In this section, we'll show that a linear equation, AX plus by plus cz is equal to d in three variables doesn't define a line in R3. It defines a plane. So why do we still call it a linear equation? Well, because the only exponent allowed is 1. So even though we still call that a linear equation in 3 space, it doesn't define a line. It defines an infinite number of lines making up a plane. Okay? So I don't know if this is the best way to think about it or not, but in 2 space, R2, exponent 1, that drops you down to 1 dimension less than 2, which is single dimension, which is a line. This one, in 3 space, maximum exponent is 1, that drops you down to a 2-dimensional structure, which is a plane, linked on a plane. Okay? So, I don't know if that helps. That's how I try to think of it. It's just a weird way my mind works, I think. Okay, so let's consider a plane, P. Now let's blow this up so we can consider it. All right. Here's a plane P. They draw a funny-looking P. Consider a plane that passes through a point x0, y0, z0. That's point P0 here. Okay? That has coordinates x0, y0, z0. We can determine P completely by specifying a non-zero vector n, and basically it's called the normal vector. Why is this a normal vector? Because it's perpendicular to the plane. Every line in the plane is perpendicular to that vector. That's why they call it normal. Now, they drew it that way. Could it just as easily been drawn this way? If it's in the same line but coming through this side of the plane, yeah, there's no reason not to. Okay? At least not yet. Okay. Okay? By specifying a non-zero vector n, we'll give coordinates a, b, c. Now, they don't show them on here. And if I write them on there, it's going to reduce it, but I guess probably I need to. So this n is equal to A, B, C. All right? Perpendicular to every line in that plane. Okay. That is orthogonal to P. Okay? Such a vector is called a normal vector. That's why they give it the symbol n. And for 2 of you who have had physics or are currently taking physics, right? And you talked about normal vectors to plane, lots of times in physics, okay? Basing n at P0, which they did here, in figure 1, we see that the point P, x, y, z, that's this point P here, and maybe since I'm now, this one is, now these are points, so you put those in parentheses, x0, y0, z0, okay? This is a point. It's the x, y, z. x0, y0, z0 says it's one particular one. x, y, z says it's a variable. Okay. Now, lies on P, on that plane, precisely when P0P, the vector P0P, the little blue vector they have there, is orthogonal to n. Anytime it is, okay. Therefore, P lies in the plane if n dot P is equal to 0, right? N, the normal vector. Now, I'm just going to write it as a normal vector, the vector. We haven't specified whether it's a unit vector or not. That's what I'm hesitating on. I'm not sure we will. Dot this with P0P, vector P0P, and that always has to be the number 0. This is a dot product. Remember Dot product of perpendicular vectors is 0. Okay? Now, this n, remember, was ABC. It's as easy as no. Dot that with, and this vector PP0 would then be x minus x0 is its x-coordinate, right? Component. Y minus y0 is the y component, and z minus z0 is the z component. Always terminal minus initial. And this is obviously the initial point P0, so the terminal point was x minus x0, blah, blah, blah. Okay. Now, that dot product is equal to 0. Right? Well, let's do the dot product. That would be A times x minus x0 plus B times y minus y0 plus C times z minus z0. And that's equal to 0. Okay? Let's write it slightly. That's a scalar equation now, right? Let's get the variables together. AX minus AX0 plus BY minus BY0 plus CZ minus CZ0 is equal to 0. That's an ugly C, isn't it? Okay. Now, variable, variable, variable. Everything else are numbers. Okay? So let's get the variables together. AX plus BY plus CZ is equal to, let's add all the others to the other side, AX0 plus BY0 plus CZ0. But guess what? That's just some number. Just some number. Okay? Now, if we just looked at this one, this side right here, that looks a lot like the dot product of this vector, and now they don't have the origin on here. Wherever the origin is, let's just put it right here. There's the origin, O. This vector would then be, because the origin, you're 0, 0, 0, so the components of this vector OP would be X, Y, Z, right? So this would be your normal vector dotted with OP. Okay? This would be your normal vector dotted with OP0. Okay? Because if you also did this vector here, that would be OP0, and that would be the vector who had components, not just coordinates, components, X0, Y0, Z0. So this is where they go next with that. Now, why they did that, I'm not absolutely sure, because where I was going with it, these are just numbers. A, B, C's are numbers, X0, Y0. The variables are these, X, Y, and Z. So this is some number, and they call it D, if I'm not mistaken. Yeah, they call this D, some number D. Okay? Now, so you could then just combine, skip the middle step here, because this is equal to D. All right. And that, by the way, is basically going to be all we need. Oh, sorry. Here's that first equation. Sorry, I didn't know they had it written in here. I'll blow it up for you so you can see it better. Okay. This is saying the normal vector dotted with any vector in the plane has to be 0, because the normal vector is perpendicular to every vector in the plane, normal, orthogonal to every vector in the plane, including P0P, okay? And this is what we just derived a couple minutes ago. The only difference is, I said, you can, rather than call them this, make it equal to D. This thing's equal to D. Or, as we said before, this is n dot OP. The vector OP would be the vector from the origin to the XYZ point. And that would then be a vector. And then this would be the vector OP0. The normal vector is always ABC. Components ABC. All right, so here's theorem 1. Finally, we got to it. Let's blow this one up too. Okay, so the equation of a plane. If you have a plane through some fixed point P0, x0, y0, z0, some fixed point that has coordinates, definite coordinates, numerical coordinates that are fixed in space, okay? The plane has got to go through that, and it has a normal vector whose, these are coordinates of the point, components of the vector, normal vector A, B, C. So the vector form of this equation then would be n dot, that vector from the origin to x, origin to y, origin to z. That, the dot product of that would be some number of d. Okay? What is that d? That d is either the dot product of n with the vector from the origin to x0, y0, z0, p0 in other words, or to calculate its ax0 plus by0 plus cc0. These are all numbers, those are all numbers, multiply them together, that gives you an add them to get d. Okay? So that's the vector form for the equation of a plane. The scalar form, and by the way, x, y, z is any point in that plane. ABC is the components of the normal vector, and that the dot product of those two things is always constant. That's not quite said properly, but yeah. Okay, scalar component, scalar form of that. A times x minus x0, that's the point from P0 to some point P in the plane. So this product plus that product plus that product is equal to 0. That basically is saying normal vector times dotted with any vector in the plane has to be perpendicular to each other, orthogonal to each other, so it has to be 0. Or another way of saying that is ax plus by plus cz is equal to b. Same thing we got down here and here. Okay. So that's what the equation of a plane looks like in 3 space. Okay? In 2 space, if it looked like this, we would call it a line. In 3 space, we call it a plane. Now, what if you had 2 dimensions? It was 3 space, but either the c or the z was 0 here, meaning that you don't have a third component in it. That's still going to be a plane. That would be your xy plane. Always perpendicular to the z plane. Okay. Now, this is just supposedly an amplification, you might say, completing the thought with that one. A note. Note that the equation ax plus by plus cz equal d of a plane in 3 space is the direct generalization of ax plus by plus equals c in 2 space. Okay? In a sense, planes generalize lines. strange statement, but I know what they're saying. To show how the plane equation works in a simple case, consider the plane P, that's this one right here, through the point 1, 2, 0. There's the point P0, 1, 2, 0. Okay, with a normal vector 0, 0, 3. Okay. Now, obviously, that normal vector is not a unit vector, so don't expect it to be a unit vector. It's just that in other contexts, sometimes we use the symbol n to represent a unit vector also. Don't think that's the case here. All it is required is it's a plane normal, it's a vector normal to that point. Okay? It passes through your point 1, 2, 0. The normal vector passes through that. Plane with normal vector n equals 0, 0, 3, got it, passing through the point P0, 1, 2, 0, is the xy plane. Okay. All this is saying is, if this has component 1 on x, 2 on y, 1 on x, 2 on y, and 0 on z, that means you're in the xy plane, obviously, okay? You don't have the z component. Especially if the normal vector passes, because you see, you can have any old plane passing through that point, infinite number of planes, okay, that can pass through that point. But if the normal vector of the plane is 0, 0, 3, in other words, parallel to the z-axis, okay, but it's going from that point, okay, then this plane has to be the xy plane because there the z is 0. Okay. So I was trying to find some sort of meaning in that beyond just the obvious. Yeah, that has to be the xy plane. Okay. Okay. I guess what they meant to do with that then is the following. They didn't really do it, but they could have. Pick some other point P here on the plane. Okay? And that point on the plane, P, this is not like the name of the plane P, P, that could be X, Y, but guess what? If it's on that plane, the Z is still 0. Okay? But these are parentheses, not angle brackets. I'm going to get the angle bracket soon, but not yet. That's just a point. Okay? Then the vector, P0P, would be X minus 1, Y minus 2, 0. It does have a Z component, but that component is 0. Okay? And then you want to dot this with 0, 0, 3. Okay? That is guaranteed to be 0. Why? 0 times this, whatever that is 0. 0 times this, whatever that is 0. And 3 times 0 is 0. So yeah, that's 0. So that means this has to be a plane. That has to be the equational plane. The scalar, the vector, what do they call it? Vector form of the equation for the plane. This unit vector crosses that plane vector, okay, has got to be 0. Okay. Which then indicates that is indeed a perpendicular line. Those are orthogonal to each other. Okay. Don't know that this has said too much so far. Oh. The equation for that plane, wherever it is, and it doesn't naturally come out of there too well, but it's okay, is that z is equal to 0. And that makes perfect sense, because notice every point on this plane, z is equal to 0. X and y can be anything in the world, but z is always 0. So the equation for that plane is simply z is equal to 0. Done. That's all. Okay. So let's move on to example 1. And I'm trying to see if this is a figure for it or not. I'm not sure I see a figure for it. Well, we'll use this whether it's the figure for it or not. Okay, find an equation of the plane through this point. P0 is equal to 310. Okay, with a normal vector, 3, 2, negative 5. Okay. All right. Find an equation for the plane through that point. Okay. Anyone want to make a stab right off the top? How would you begin? I would begin at the end of the first theorem. Notice the last thing it says, where d is equal to this. You're giving the points. This is your x0, y0, z0. This is your point, the components A, B, C. Okay? So that last sentence there where d is equal to, let's do that first. D is equal to what? A little louder. Okay. You may have said it right. I didn't understand it. The n values? Is that what you said? Okay. All right. Yeah, those are your A, B, C. There's your A, there's your B, there's your C. Here's your x0, y0, z0. So what is your D equal? Yeah, multiply them. That will give you, second, 9 plus 2 plus 0, so that's going to be 11. So there's a D, okay? Now, and then all you have to do is write down your ABC with the x, y, z. Now, this isn't the x0, y0, 0, your equation 5 up there in page 665. I assume it's that in your book too, that third equation, yeah. And then you just say 3x plus 2y minus 7z is equal to 11. Once you know what d is, basically write it down. These are the coefficients of your point P, which is x, y, z. So 3x plus 2y minus 7z is equal to that d. That's your equation for y. Okay? I'm sorry, for a plane, for the plane that has that as a normal vector through that point there. Okay?
Your C is supposed to be -5.
Oh, is it? How did that become -7? I don't know. What were you doing to make that, huh? Okay, sorry. Out of the blue. Okay, -5. All right. And sure enough, that gives us 3x plus 2y minus 5z is equal to 11. Okay. Pretty straightforward. If you know the normal vector, you can write it down. If you know the normal vector and the point, you can write it down. Now, do you think if you knew the equation and the point, you could write down the normal vector? You should be. If you got 2 out of the 3, you should be able to figure out the third one. Or if you had the point and the equation, could you come up with the normal vector? So those are things to ponder for later. Okay. Now, this is part of conceptual insight, I think. Keep in mind that the components of a normal vector are lurking inside the equation for that plane. They're the coefficients. Those are the components for the normal vector. 3, 2, -5, if I get the -5 right, okay? Those are the components. They're right there in the equation, blaring at you. The same is true for lines in R2. The line AX plus BY is equal to C in this figure here. Let's see if we can blow that up a little bit. We'll probably get a little bit of that other thing in it, but we don't care. Okay. The line AX plus BY equals C, that's the greenish kind of line there with the blue in the middle, okay? That's that line, AX plus BY equals C. This is in 2 space now, XY plane, R2, no R3 here, okay? The line AX plus BY equals C has a normal vector, believe it or not, of AB, because the line has a slope minus A over B. Okay, we'll just leave that alone. And the vector N has a slope of B over A. Those lines are orthogonal if the product is on the if the product of the slopes is -1. Okay? That means perpendicular. Does it? Yeah. Perpendicular, the product of slopes is always -1. In other words, one slope is a negative reciprocal of the other. You knew that before. Now, the thing is, we're not used to thinking of a normal vector to a line, but indeed that's the case. And their drawing it doesn't make it necessarily true, but indeed it is true. Okay. That's just a conceptual insight. Note that if n is normal to the plane P, then so is every non-zero scalar multiple lambda n. When we use lambda n instead of n, okay, the resulting equation for P changes by a factor of lambda, which makes sense. For example, complete the following two conditions. define the same plane. Okay. This is just, it doesn't seem very earth-shattering here. X plus y plus z equal 1 is the same plane as 4x plus 4y plus 4z equal 4. I mean, all you've done is multiply by 4. The first equation uses the normal 1, 1, 1. The second equation uses the normal 4, 4, 4. They're just multiples of each other, so they're collinear. Okay. On the other hand, two planes P and P prime are parallel if they have a common normal vector. Okay? And here are examples of this. X plus y plus z is equal to 1. X plus y plus z is equal to 2. X plus y plus z is equal to this. Do it 7. Okay, why they jumped to 7, I don't know, but they did. It's fine. Oh, I'm sorry. That last one, they just said 4x plus 4y plus 4z. Okay, doesn't matter as long as those are multiples of each other. Okay, those are parallel planes. Now, think back to your line example we just had. All you had to do here was change the y-intercept, but keep the slope the same. They all would have had the same normal vector. It's just ax plus by is equal to c. That could be one c, that could be another c, that could be another c, that could be another c. All you're doing is changing, and those are parallel lines. Do the same thing with the planes, and even multiply them, because you could have 2ax plus 2by is equal to 2c. That would still be the same plane, or the same line as this one. And that's all they've done here. What they did over there, they've made parallel planes. Okay? You're just different. The planes are all parallel, but they're cutting through space in different places. Okay. They'll never intersect. Okay. In general, a family of parallel planes is obtained by choosing a normal vector n, ABC, varying the constant d, and that gives you your normal plane. The unique plane in this family through the origin would be ax plus by plus c is equal to 0. So let's do example 2. I think we can. Let's see if there's a... I think this is the figure for it. So we'll do it on this one. And let me see. Oh yeah, we got plenty of time. So let's let P have an equation. P is a plane. And here's the equation for that plane. 7x minus 4y plus 2z is equal to negative 10. I'm going to ask a really dumb question first. What's the normal vector to that plane? I don't know what that plane looks like. I don't know where it is. But what's the normal vector to it? Come on, was I just flapping my gums earlier? Look right under Theorem 1. It says, note that the equation ax plus by plus cz is equal to d, okay, of a plane in 3 space is in the generalization of the equation that blah, blah. Okay, sorry, that's not what I wanted you to look at. I guess the Theorem 1 itself. The normal vector in ABC, those are the components of it, and the scalar form of the equation of that plane is ax plus by plus cz is equal to d. Okay, with that in mind, can you give me the normal vector for that plane? I don't even see it as being very murky. What is it? What was it in that one? The normal vector is ABC. You see Theorem 1 there at the top of page 665 or somewhere thereabouts? Okay. ABC. The equation for that plane is ax plus by plus cz is equal to d. Now what was the normal vector? Ah, yes! Your normal vector here for this plane is 7, I can't write. You see? That's what we've been talking about, or I've been talking about for a long time here. 7, negative 4, 2. It's right there. You know, screaming at you. It says lurking, okay? Where was it? It said lurking. I know I read that. Oh, there it is in Conceptual Insight. Okay, that's the one I meant you to read. Okay? Find the equation of the plane parallel to P, this is P, parallel to P, that passes through the origin. I think I can do that one. Okay? If it's parallel to P, what's the same? Anything? If it's parallel to P, what's the same as that one? Anything? Okay. Second? The coefficients are exactly the same. It's the same normal vector. You're exactly. And if it goes to the origin, guess what that constant's got to be? 0. Okay? So the one that goes through the origin is 7x minus 4y plus 2z is equal to 0. That goes to the origin. Now, why is that true? Because this dotted through the point that's on the plane, any point on the plane, that's got to equal 0. That's your D, right? That's how we got that, right? And what's the only way you can get that to be 0? If all those are 0. So if it goes through the origin, the constant D has to be 0. Okay? Now, find the equation of the plane parallel to P that passes through Q. Q is a point now. And this point Q is 2, negative 1, 3. Find the equation of the plane that passes through that point. Same normal, so you dot 7, negative 4, 2 with this thing. The thing from the origin to this point that would be the vector 2, -1, 3. Okay? And what's the dot product of those two? 14 plus 4, 6, which is 24. So the equation that goes through here is 7x minus 4y plus 2z is equal to 24. Right? That's it. Okay? And here we have it, in case you aren't really wanting to work any. There's your original one, the dot product of the vector through here, origin to here, and your normal vector is got to be -10. That would be down there. Through the origin, that would be that one. And 24, that would be somewhere out there. The normal vectors are all the same. That's why the coefficients are all the same. All that changes is the constant d, and you get d by dotting the normal vector by the vector that goes through from the origin to that point, whatever that point is. Origin, 0, 0, 0, that point. Now, what we don't know is where that first one crosses, but do we even really care? They have a -5 in there, so I'm guessing they may be saying it crosses there, but, you know, frankly, who cares? Okay. Does that make sense? That was example 4. Was it? I've lost where I was. No, that was example 2. Okay. Looking on the wrong side of the page. Yeah, got it. Now, where is that? This is the equation for any plane parallel to the plane we started with. All you do is change the d, okay? And if you want the origin to fit there, just plug in 0, 0, 0. So you don't even have to dot it. If you want the origin to be on that plane, all these planes with any d there, they're parallel to each other, right? So if a point passes through some x, y, z, like 0, 0, 0, then d is going to be 0. That one we just did, plug in the value, that's going to give you your d. All you have to do is plug in for the x, y, and z. That's going to give you your constant. Now, points that lie on the same line are called collinear. And if we're given 3 points, P, Q, and R, that are not collinear, well, let's see if there's any other slide here. I do not see, oh, there it is, yeah, that's figure 5, okay. If we are given 3 points, P, Q, and R, that are not collinear, then there is just one plane that passes through P, Q, and R. Now let's step back to 2 space again. How many points did it take to define a line? 2. You've got to have 2, okay? Now, if you had 3 that were not on the same line, that basically defines the whole plane, or spans the whole plane. So basically what you need is 3 points that are not on the same line. That defines a plane, any plane, okay? Now, the next example shows how to find then the equation of that plane. Okay, now if you remember, back when we were in a plane and trying to find equations for a line, we could do 2 points could give you an equation for a line. A point slope would give you a point for a line, or a slope intercept gave you an equation of a line. 3 ways. All you needed was 2 pieces of information, and you can get an equation for the line. Okay? In a plane, you need 3 pieces of information. Either, Let's do it with 3 points, okay? And here's example 2. Point P is, they don't put them here, so let me do. P is the point, now these are points, these are parentheses, 1, 0, -1. Let's see if that could possibly be, no, that doesn't look like this point, because the X doesn't look like that's 1, the Y doesn't look like it's 0, and okay, so this is not the thing, but it's okay. Here's another one, Q, a point, and that's 2, 2, 1. And here's R, yeah. R is the point, 4, 1, 2. Okay. Now, I guess you first need to show they're not collinear, but for them to be collinear, we'll just assume they're not, okay? 3 points that are not collinear. Okay, find an equation of a line determined by those points. Okay. Now their figure here gives you a hint. Okay? Even though these aren't the same points, but that figure should give you the hint. The what? Okay, well, the plane has a normal vector. If we can find the normal vector, we've got the plane, right? Because we've got a point. All you need is the normal vector in any point, right? So if we can find the normal vector, we've got it. What does it mean to be normal? Okay, not talking about people. Okay, what does it mean for a line to be, or a line to be normal to a plane, or 2 lines to be normal? What does that mean? Orthogonal, right angles. Okay. Now, what produces always something that's right angles? A cross product produces a vector that's right angled to the 2 vectors you're dealing with. So if we have 3 points, pick any one of them, I don't care which, let that be the initial point, and then go to the other 2 points, right? Yeah, let's let point P, they did there. So you give me vector PQ. What would that be? That's going to be a vector now, because initial point P, terminal point Q. What would that be? We've done this way back, didn't we? 1, good guess. 2, very good guess. Second, 2. Okay. Now, let's come up with another vector. Guess what? We want it to have the same initial point. Okay? We're happy with that, aren't we? Okay, so let's do another one. Maybe PR, public relations, right? What would that one be? 3, second, 1, 3. Now, at this point, you should be able to tell me whether these are collinear. If they were collinear, what would those have to be? Multiples of each other. Can't you see those are not multiples of each other? Right? Because one, just pick the first one. This is 3 times that. Well, that's not 3 times that. That's not 3 times that. So these are not collinear. So if you do this, even if you don't know if those 3 points are collinear or not, do this process, and then it'll be obvious whether they're collinear. Okay? So these are not collinear. So guess what we're going to do with those 2 vectors? Cross them. Okay? Get on the bad side. Now, do you remember how to cross the vectors? How? I, J, K. And then write the vectors down. 1, 2, 2, 3, 1, 3. Okay? You want to string it on out like I like to, or you want to do it another way? IJ, 1, 2, 3, 1. Okay? Let's do the I's. The I's have it. 6 minus 2. I. Let's do the J's. 6 minus 4 plus 2J, right? And do the K's. 1 minus 6 is minus 5K. Did y'all do that okay? Was I going too fast? Did everybody see how I did that? Okay. What does that give you? What does that give you? Just about. That gives you the normal vector. That is the normal vector to that plane. See? This is your n. A normal vector to the plane. Now how do you get the equation? Okay, let's do the equation for the plane. The equation for the plane would then be 4x plus 2y minus 5z. Have we had this one before? We had a minus 5z before. Oh, I can't see it. No, that was 3. That was 3, 2, negative 5. This is 4, 2, negative 5. I thought that looked awful familiar. Okay, and that's equal to some number. What do we call it? B, wasn't it? Okay, B. How can we get that B? Oh, what was it? D. Okay, I can't hear. Okay, D. That sounds better. Okay, yeah. A, B, C, that's D. Okay, got it. How can we figure out what that D is? Say again? I can't hear you. Yeah, you could do a dot product, but even easier than that. And it's really that. Plug in that term, that initial point, P, plug in for X, Y, and Z. That's really what the dot product would have given you, right? So plug it in, plug it in. What does that give you? 4. Oh, I was going to do that one. Second, 0, I got it. Plus 5 equal 9. D's equal to 9. Okay? So what's your equation for the line? For the plane? 4x plus 2y minus 5z equal 9. That's it. Now, yep, there it is. 4x plus 3y minus 5z is equal to 9. Okay, let's see if we can get example 4 done. I don't think we have a slide for that, so I'm going to erase this. Any questions on that one? Okay. Example 4. Find the point P where the plane 3x minus 9y plus 2z is equal to 7. Is that a plane? Yea or nay? Yeah, of course it is. Find the point P where that plane and the line R of t, this is written as a vector, which is, remember how we did them like this? 1, 2, 1 plus t times negative 2, 0, 1, where they intersect. Okay? Find the point P. We're looking for some point P where that plane and that line intersects. Okay. Excuse me. What's that? Yeah. Yeah, we did it way back. Okay. Now, I hope this isn't too confusing. How they are approaching this is, I hope this isn't too confusing, that point where they intersect be the point XYZ, kind of, right? Okay. Now, for this line, what's the x component for this line? This r of t has components. I want to call them something else, but let's call them x, y, z. Okay? And what would they be? 1 minus 2t is the x value, x coordinate. Say again? 2 is the y coordinate. 1 plus t is the z component. Okay. All right. So that's done that. Now, that line must cross this plane. So those x, y, and z values must be the x, y, and z value of that plane, right? So let's plug those in. 3 times 1 minus 2t minus 9 times 2, that's pretty easy, wasn't it? Plus 2 times 1 plus t, that has to equal 7. Is that making sense? Well, let's see what comes of that. It would be 3 minus, y'all can do the math, can't you? 6t minus 18 plus 2 plus 2t is equal to 7. Let's combine like terms. Here we have 5 minus 18 would be minus 13 minus 4t is equal to 7. I think I'll subtract 7 from both sides and add 4t to both sides. So I've got 4t is equal to, I believe it's negative 20, isn't it? T is equal to negative 5. Okay? Now, the point then, x, y, z, that's where it's going to be. And what is your x then if t is equal to negative 5? 1 plus 10, 2, 1 minus 5. Okay? Now, I really shouldn't have angle brackets there. This would be 11 to negative 4. I'm guessing that's it. Okay? And how do you check that real quickly? 33 minus 18. You want to do that in your head fast? 33 minus 18. Maybe not. 15. Is it? 15 minus 8. 7. It works there. Let's see about here. Is this on this line? I think we just showed it had to be. Yeah. Because when t is equal to -5, it's on that line. So, sure enough, I think we got it knocked. Let's see if they got the same thing in the third. Yeah, the point was 11 to -4. Good for them. Okay? And we will begin next time at the paragraph right under example 4, just before, and we came that close to finishing the chapter, section. Okay? Homework exercises, do any of the odds 1 through 7. Do any of the odds either 9 or 11 or both if you choose. Either 13 or 15 or both if you choose. Either 17 or 19 or both if you choose. Any of the odds 21 through 27. Any of the odds 21 to, 21 to 27. Then do 29, okay? Then any of the odds 31 to 35. Do 37. And then finally do either 39 or 41 or both if you choose. And we'll stop there and pick up the rest of them later. Good deal. Making sense? Okay. We'll catch you next week. Have a good weekend.